So hello, everyone. Good morning here in Hong Kong and good evening, Yann, in New York. Thank you for being our guest today at the Center for AI Research webinar. It's been maybe 2 years since your last webinar for us.
Something like that.
A lot of things have happened since then in the field of AI. And I'm sure many students and other even faculty here are very excited to listen to what you have to say. So today we are going to talk about your view on the latest large language models, so whether we really need to have really needs to have sensory input in order to be really understanding humans and be intelligent, because there are a lot of voices out there saying yes, saying no. So let's hear your view, and afterwards we'll have a chat, and then we'll give a chance for the audience to ask questions in the Q&A session. So welcome, Professor Yann LeCun from NYU and Chief AI Scientist from Meta. I don't think you really need introduction, but here you are. Welcome, and we look forward to your talk.
All right, thank you, Pascal. Thank you for having me on. Okay, let me share my screen. All right. Okay, so I'm going to spoil the whole question from the title and immediately answer yes. Do large language models need sensory grounding for meaning and understanding? And the reason is that despite what we might be led to believe, we are still very far from having machines that have human-level AI. The machines that we have at the moment are extremely fluent. They can manipulate language very well, but they have some limitations. So I'm going to talk about this now. And, I'm being sort of deliberately negative here, because as a scientist, you always have to find faults in everything so that you can move forward. You have to figure out what's wrong with something before you can move forward. And to a lot of the world, generative models are very new, but for many of us, they've been around for a while, so they're not that new. And so we've already thought about what's wrong with them. Okay, so first thing we need to realize is that machine learning in general really sucks compared to what humans and animals can do. Supervised learning, of course, we all know, requires a large number of label samples. Reinforcement learning requires some ridiculously insane amounts of trials to learn anything. And of course, self-supervised learning, which has made a lot of inroads over the last several years, works really well, but it requires a large number of unlabeled samples. So most current machine learning-based AI systems basically make really stupid mistakes. They don't seem to understand how the world works the way animals and humans do. They don't seem to be able to reason very deeply or plan, unless the plan has been, somehow similar plans have been present in their training data. And it's a far cry from animals and humans, who can learn new tasks extremely quickly, understand how the world works, can reason and plan, have some level of common sense. And current machines, not so much, or at least a very limited type or superficial type of common sense. Okay, so self-supervised learning certainly has taken over the world over the last few years for understanding and generating images, audio, and text. And the idea of self-supervised learning is very simple. You take a piece of data, for the sake of the example here, let's say video. You hide a piece of it, show a piece of it to the system, and then eventually reveal the rest, and the system trains itself to capture the dependency between the part that it sees and the part that was previously hidden. So capturing the dependency may mean predicting, but it doesn't necessarily mean predicting. And it doesn't necessarily mean predicting the future. It might mean predicting the past, or predicting things in the middle, or part of an image, for example. And this certainly works really well for natural language processing and text. So the standard way for now several years, 5 years, to train natural language processing systems is you take a piece of text, a window over a corpus, typically several hundred or several thousand words, you corrupt it in some way by masking some other words or by replacing some other words by others. And then you train a gigantic neural net to predict the words that are missing. And in the process of doing so, the system learns internal representations of text that can be used for any kind of downstream tasks, such as translation or topic classification or summarization or anything you want. So that works amazingly well. It's really surprising. And there's a special case of this in which you only predict the last word. So you don't predict missing words taken at random. You only mask the last word and you train the entire system to just predict the last word. And this is really what an autoregressive generative model is. Now, in fact, the term can be applied to all kinds of different models that don't necessarily generate text. They can be generating also images, or video for that matter. But basically, think of we're going to call this a token. A autoregressive generative model takes a window of tokens, encodes it, runs it through some sort of predictor, which may be stochastic, and then produces the next token. Then that next token is shifted into the input, and the process starts again to produce the next token. It's autoregressive because the previous outputs are fed into the inputs, and to predict the next one. Now there are issues with this particular architecture, and this is the model according to which, I mean, this is the kind of architecture that is used by essentially all LLMs and dialogue systems and text generation system, whether it's older ones like Blunderbot or Galactica, which was a system put together by my colleague to help scientists write papers. Llama, which recently came from FAIRE, that's open to researchers. Alpaca, which is a fine-tuned version of Llama. Lambda and Bard from Google. Chinchilla from DeepMind, ChatGPT from OpenAI, GPT-4. We don't exactly know because there is no information about it, but chances are that it's also an autoregressive LLM. And the performance of those systems, if you do it right, if you make them big enough, if you train them on enough data, is absolutely amazing. They do things that you would not suspect a system trained to just predict the last word in a window of text would do. But as amazing as they are, they make very, very stupid mistakes. They make factual errors, they make logical errors, they are inconsistent if you ask them to produce long sequences of words. They have very limited reasoning ability. They have you have no way of controlling whether their output is toxic according to whatever criterion you want. They're not very controllable because what they produce is entirely determined by the statistics of the training data and by the prompt. There's nothing else. They have no knowledge of the underlying reality that language is supposed to describe. They have no common sense, and they can't really plan their answer. They put out their tokens autoregressively one at a time, and there is no sort of look ahead, if you want, to predict what's gonna be predicted or predicted before it's predicted. So those are limitations, and those are limitations that create an issue here, because if we imagine the set of all possible token sequences, okay, let's say word sequences, it's a tree, okay, we can organize that as a tree, and within this tree there is a subtree that corresponds to all the answers that are correct according to some criterion for the prompt that was given to the system. Now, let's imagine that there is a probability E that any produced tokens takes us outside of the set of correct answers, okay? And because those are trees, once we get out of that tree, we can't go back. There's no way back, okay? So let's say this is the probability of getting out of the correct tree. Then as we produce more and more tokens, the probability of staying within the correct set of correct answers is 1 minus e to the power n. The probability of staying within the set of correct answers decreases exponentially. So if you think that the way to fix this is to make e very small, I can always find an n for which this will not be negligible. So this is an exponentially diverging process. which is not fixable. It's not fixable as long as we keep those systems, as autoregressive token prediction. So it's not fixable without a major redesign. So I have a prediction here, which is very unpopular, which is that within a few years, perhaps as short as 2 years, nobody in their right mind would use autoregressive LLMs because of that divergence and hallucination problem. This is one reason why those systems hallucinate. It's not the only one, sadly. So, they're amazing, but they kind of suck. They have a constant number of computational steps between input and output. For every token that is produced, there is a fixed number of computational steps taking place. So it's kind of a weak form of reasoning, if there is any. You can't spend more time reasoning about an answer with those systems if it's a more complex problem. It was always take exactly the same time to produce one token. And there's no real reasoning in that sense, in the sense of when we reason, we spend more time solving problems that are more complicated. There's no such possibility with autoregressive LLM. And there's no planning. Whereas all those things exist in animals and humans. In fact, they exist more in animals than we think. So understanding the world, or how the world works, predicting consequences of actions, performing chains of reasoning with unlimited number of steps, and planning complex actions by decomposing them into sequences of subtasks. So how do we get AI systems to be more like animals and humans? That would be useful because there is a vision by which in the future we'll need to interact with virtual assistants, and the more human-like they are, the easier it would be for us to interact with them. So one question we can ask is, how do babies learn how the world works? And they mostly learn by observation. And most of the knowledge that they acquire in the first few months of life is completely non-linguistic. And obviously it's true of animals, but it's also true of humans that much of our knowledge is not linguistic. Linguistic is kind of a layer on top of a basic knowledge that has to do basically with physics. So learning things like gravity, inertia, conservation of momentum, basically have intuitive physics notions. That happens in human babies around the age of 9 months. There are other things, very basic things that occur before. And what kind of learning is taking place when babies learn everything about how the world works, where they have a mental model of the world that's incredible by the age of 2 or 3. And that, as we grow up, that allows us, when we become teenagers, to learn to drive a car with a relatively short amount of practice, whereas we still don't have self-driving cars, despite GPT-4 or whatever it is. We don't have self-driving cars. We don't have domestic robots that can clear up the table and fill up the dishwasher. So obviously we're missing something big in terms of artificial intelligence, despite the fact that we have amazing systems that are very fluent with language. So I see 3 challenges for AI and machine learning in the future. One is learning representations and predictive models of the world, but not just text, also video, visual inputs, and perhaps audio. Of course, using self-supervised learning, learning to reason, and learning to plan complex action sequences. These are 3 things that autoregressive LLMs today cannot do. And they're pretty basic. And by the way, this slide is much older than any LLM that we have. I've had this slide for several years. So these are not new problems. So one proposal I've made, which I've published in Open Review a while back, is perhaps a vision for where sort of AI research should go over the next few years, independently of potential commercial success of autoregressive LLMs. And it's based on what's called a cognitive architecture, which a lot of people have proposed in the past. And it's essentially centered around this idea of world model. So rather than explaining what this entire diagram is, I'm going to describe how it's used in a very simple case. So the system observes the world, gets percept X, that goes into an encoder, basically a perception system that produces a representation of the state of the world. Let's call this S0. And then what we're going to do is the system is going to use an internal world model that is called here a predictor to basically predict what is going to be the state of the world at time t+1 if I know the state of the world at time t and I take the action A at time t. And I'm going to imagine that I'm taking a sequence of actions and then imagining the resulting state of the world that will result from my sequence of actions. The state sequence is going to go to a bunch of cost functions, and the entire purpose of the system is to find the sequence of actions that minimizes this cost function. So this model is very old. It goes back to the 1960s in optimal control, and it's called model predictive control. So you have an internal model of the world, imagine a sequence of actions, and then optimize that sequence of actions to minimize a set of objectives that are hardwired into the agent. And then once you figure out that sequence of action, you just output the first action or the first two actions, and then you replan. Okay. Now, how you do this optimization, I'm not going to go into this. There's a bunch of work, along those lines, using learned models, particularly things like Denija Hefner's work on Dreamer, V1, V2, V3, some old work by students and me and others. And then the question is, what goes into this cost function? And I think this addresses a problem that a lot of people have been asking themselves today, which is, how do you get an AI system to produce outputs that are aligned, that are controllable, and that are aligned with human values? Like if you want the system to answer a question, you probably want that answer to be factual. If you ask it to produce poetry, you don't care. If the system talks to a 13-year-old, you want to produce an output that's understandable by a 13-year-old. So you would like to, and you want probably the answer to not be toxic and things like this, right? To be age appropriate, to be appropriate for the culture of the person that is being interacted with. So you'd like to be able to put all of those criteria into the cost function. And because the system at runtime optimizes this cost function, it makes the system controllable. This is very different from an autoregressive LLM where you don't have such a cost function. The cost function is implicit through the statistics of the training data and through the prompt. But there's no explicit cost function that the system has minimized. So as a consequence, that makes them non-controllable, possibly non-factual, possibly toxic, and divergent for long sequences of tokens. So this may be a solution to that problem. Now, I can't give you an example of how you do this in the context of text. People have done experiments with this, but mostly for things like robotics and control, not so much for text generation, although there are a few papers on this topic. So the cost function would be composed of two subcomponents, one which is a sort of immutable intrinsic cost that really, you can think of it as kind of safeguards, safety costs that prevent the system from producing things that you absolutely don't want it to produce. And then the trainable part, which is similar to what people currently call reward models that are basically trainable costs that can be adjusted for the system to produce good answers. Okay, so now how to build the word model. So there's a big issue here, which is that although predicting the next word can be done because it's easy to represent uncertainty in sort of discrete outputs like words, it's very hard to represent uncertainty prediction for things like video. So if we want a system to be able to learn how the world works by watching videos and training itself to predict what's going to happen next, we're going to have a way of representing uncertainty in a video. And if you don't do this, if you just train a big neural net to predict what the next frames in videos, you get blurry prediction like the little animation you see at the top and the picture you see here in the second column. So we're going to have a problem with generative models when predicting or when using self-supervised learning for images. And in fact, when you want to train a self-supervised learning system to recognize images, the best systems do not use generative models, with one exception. But the best systems really use what's called a joint embedding architecture. So what's a joint embedding architecture? It's an architecture where if you have X, the observed part of the video, and then Y, which is the thing you want to capture the dependency of, you embed both of them through an encoder, and then you do the prediction in the representation space. And that allows the system to basically eliminate all kind of irrelevant information from the input so that the prediction is easier to make. Now, how to train those systems wasn't clear until a couple of years ago. And I would not have believed that something like this could work until a couple of years ago. But now we have a bunch of algorithms that actually can train them. So I'm just going to give you an example of a couple. Skipping ahead a little bit. But before that, this type of architecture cannot be modeled as a probabilistic model, because there is no real probability of Y given X that this system can model. So I'm going to ask you to abandon generative models. I just ask you that in favor of those joint embedding architectures. Abandon probabilistic modeling. Abandon contrastive methods, because the methods that we use to train those things are non-contrastive. And also abandon reinforcement learning, but that I made a point before. And so let me just give you one example of how you can train those systems. Basically, you need to have a way to prevent them from collapsing. So basically, to prevent the encoder from just ignoring the input and just producing a constant output, which would be trivial to predict. And so you have to basically maximize the amount of information that comes out of the encoder to some measure. And one measure that we found is something that we called variance covariance regularization. And if you have this predictor, that's an invariance term, so that's called variance invariance covariance regularization. And I'm not going to go into the details of how this works, but basically you try to make sure that the variables coming in SX have non-zero variance and are uncorrelated with each other or independent from each other. There's a bunch of papers on this, some of them quite recent, and it works really well for image recognition, for optical flow prediction, for depth prediction. Here's another slightly different type of architecture, but I mean, same architecture, but different type of training algorithm called image JAPA, which that's on arXiv. You can look at the paper, which works really, really well for learning image features. But I want to conclude by saying that if you have this kind of JAPA architecture, you can use it as the basis of a planning system that can make long-term plan. So let's imagine that we're observing the world at time 0, x0, that goes to an encoder, extracts some representation of the state of the world. We can make predictions, but if the state of the world here is very informative, the type of prediction we can make is really short-term. If we try to make long-term prediction, it's not going to be very accurate. So what we can do is stack a second layer, run through a second encoder that produces a more abstract representation of the world, and with which you can make longer-term prediction. So, for example, if I plan to go from New York to Hong Kong, I can tell that within 24 hours probably I'll be in Hong Kong, but I can't. And I can decompose this into very simple tasks, like I need to go to the airport, catch a plane to Hong Kong. How do I go to the airport? Well, I'm in New York, I need to get down on the street and catch a taxi. How do I catch a taxi? I need to, how do I get out on the street? I need to get out of my chair, get out of my house, blah, 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 right? And, ultimately we decompose this complex task into simpler and simpler one, all the way down to millisecond by millisecond muscle control. And that's the idea of hierarchical planning, which is complicated to do under uncertainty, but that's basically what an AI system will have to do. And I'm sort of proposing a sort of vague architecture that would allow to do this, but I can't tell you that it works. I can't show you results that show that this hierarchical planning actually works. Okay, so I'm done. So we need grounding for AI systems. Current AI systems, although they are fluent and can manipulate language, they have a very superficial understanding of the underlying reality. They have very limited abilities to plan and reason, And we need systems that are much better at this than the current systems that we have. Thank you very much.
Thank you, Yann. I have so many questions. So on one hand, this is a very, very almost like intuitive, I think. I think people will always agree that, intelligence systems need to have sensory input and so on, and grounding. On the other hand, this just raises more questions. I think one reason people like all these generative models is just so simple. I know that the company SenseTime, the Chinese company SenseTime, they when ChatGPT was launched, they immediately went into like training their own generative models in November, right? And by now they announced that they already came out with, textual model, large language model. They have the image models, they have multimodal, everything, right? And I don't think they even need like anybody who has experienced NLP or experiencing in vision. You can just train, you just have machines and you train them, right? So I think that's one thing that makes people feel like, oh, and then people are kind of expectations exceeded, because then, wow, it can do so many things. And we keep discovering emerging capabilities. And the simplicity of autoregressive models is astounding. What you propose to us, I think it's very, very, makes a lot of sense, but it raises the question. For example, like I'm in natural language processing, right? For example, let's say conversational AI systems. When you talk about the actions, right? I can imagine it must be like the next turn of conversation and so on. But when I train, how do I know which part, what are the subtasks? In traditional AI in the long time ago from 60s, 70s, there's another traditional AI approach where they say, they use symbolic methods to do the planning, the subtasks and so on. That didn't work, and it's not going to work because all these symbolic methods depends on human design of this subtask. So how can we still have very powerful self-learning in a way? Neural networks in general is self-learning. We don't have to do intelligent design of features and so on. How can we take advantage of that and yet adopt your model of this subtask and the planning and so on? How do we do that? Can you?
Right. So the idea behind the architecture that I presented is that if every module is differentiable, including the predictor and the cost functions, you can do the planning through gradient-based methods. Okay, gradient descent, basically, right? You backpropagate gradient from the cost through the predictor all the way down to the actions, and by gradient descent, you can figure out optimal sequence of actions. Now, people in optimal control know very well that this doesn't work very well if you have a long sequence, and if the predictor is very complicated, very nonlinear, blah, blah, blah. You get stuck in local minima, blah, blah, blah. So you have to use all kind of tricks for that kind of optimization to work. Or you have to do it hierarchically, right? So let me take a concrete example. If I want to plan a trip from New York to Hong Kong, visiting you in Hong Kong, and have to do it in the space of muscle action, which basically is millisecond by millisecond or 10 millisecond by 10 millisecond, it's impossible, right? I can't do this plan because first of all, I would have to know all the details of all the situations I'm going to encounter. I'm going to have to cross the street to get to Third Avenue to catch a taxi. Is the light going to be green or red? I can't predict any of that, right? I'm going to have to get around a particular obstacle, blah, blah, blah. So I'm not going to be able to do the whole plan, but I can do a general plan at a high level, very abstract level, which is I need to go down the street, catch a taxi, go to the airport and catch a plane to Hong Kong, right? So that's a high level plan. There is very few details about it, but I have a first task now I have to accomplish, catch a taxi, right? And then how do I catch a taxi? I go down in the street. How do I go down in the street? I get up from my chair, go to the door, open the door, blah, 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 right? Etc. And then at the bottom level, I can do the millisecond by millisecond planning of how to get out of my chair. So hierarchical planning is a necessity if we want systems to be able to accomplish intelligent tasks. And again, LLMs don't do this at all.
Well, there is an argument that, for example, with GPT-4, it's already learning multimodal input, right? So you can say that's grounded in sensory input, at least from image and I don't know about video, but at least from image.
Probably not video. It's
not video.
Certainly some form of images, probably tokenized images, so that they look like text.
Yeah, and the images are also like some kind of joint embedding, right? Because you've got an image and the text embedding, binary model embedding together. So you can argue that, and ChatGPT does perform much better than GPT-4 does perform much better than ChatGPT. Now we don't know whether it's because of more reinforcement learning, more human feedback, or is it because it's really doing multimodal learning? Like whether the ability comes from which side? Probably from all of this.
Probably some combination.
Yeah. So probably that the multimodal learning is enhancing its let's say enhancing its reasoning or planning, if there's any. And again, coming back to your example, so I'm just thinking, like, suppose I want to train this model, right? So that means like I'm gonna have world model from video, from image, from text, from audio probably, or everything that's possible to get. And then we're gonna train lots of different kind of tasks and subtasks, right? Because for example, for each video or for each dialogue, they have their own tasks, and some other dialogue, some other video will have its own subtask. So we'll be training all of this subtasks. So with all of this data, and then hopefully, like when we are performing a task that we have not seen before, it will automatically know which subtask, right? And then it will do
right.
Yeah.
Because hopefully it would have learned hierarchical representations of action plans.
Yeah.
There's something also important about the architecture I'm proposing here, which is that you change the task by changing the cost function, right? So the task is entirely determined by the cost function. So one term in the cost function could be, is the text a good continuation for the prompt or something, or is it a good answer to the question in the prompt? But then you can have other costs that correspond to things like toxicity or complexity or length or whatever it is, or whether it should be poetry or something else, right? So you can control the system not by prompt engineering, but by just specifying a cost, right? And what that allows is that now the model itself, the predictor, the world model, is task independent. So it's not the case for current LLMs. Current LLMs have to be trained to do everything at once. They have to be trained to so that they do the right task when you specify that task in the prompt. This is the instruct GPT type training. They have to be trained so that their outputs are pleasant or useful or non-toxic, which is the RLHF procedure, right? Reinforcement learning through human feedback. And in the end, that's kind of compiled into the model. All of this desires, right, of all the tasks and situations, blah, 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 those have to be compiled into the weights of the system. Whereas in the architecture I propose, the task is not in the model. The task is in the cost. The model, through inference, produces answers that optimize that cost. So that's kind of, I think, a major difference. If you think about this process of inferring the value of unknown variables to minimize the cost or maximize the likelihood, whatever you prefer, is very similar to what people are talking about or were talking about in the context of graphical models and Bayesian networks and probabilistic inference. You have a bunch of you have a model that essentially captures the dependency between a bunch of variables. You're given the value of some of the variables, and you have to infer the value of the remaining variables so as to either maximize the likelihood, or in my case, minimize an energy, but it's the same thing conceptually. That's a much more powerful computational tool than autoregressive generation, because it's Turing complete. So autoregressive generation is not Turing complete in the sense that if you have a finite number of operations that will allow you to that you can use to produce a token, a fixed number of operations, which is basically the number of layers in your transformer. There is a limited number of functions you can represent with a finite size of your model.
Even when it's trillions and trillion parameters, it's finite, but it's trillion.
It doesn't make any difference. It's never going to be Turing complete because it's finite. The representational power is limited by the size of the transformer, even if it has a trillion parameters, and the number of computational steps you can use to generate a token is fixed, right? Now, in the model I propose, it's very different. Now you have a process that minimizes an objective with respect to a bunch of variables, and that is much more powerful computationally. You can basically reduce any process you ever thought of that you can do with a computer as minimizing some sort of energy function, right? Anything a computer produces can be seen as the minimum of some energy function. That may not be easy to minimize, but that's beside the point. But inference, any kind of inference, can be viewed as the minimization of some energy function. Okay. In the end, that process, can take a long time, can be very complicated, can not converge, blah blah blah. But that's much more intrinsically more powerful than just generating a token after another.
So you were talking about we should give up generative models and we should give up probabilistic models. It is going to be very hard for people to give up the large language models, diffusion models. So I'm going to ask a contrarian question. Is there any way we can, use the power, take advantage of the power of the language abilities of these models with the schema you propose?
Sure. Yeah. So that's the challenge. How do we get machines? How do we come up with an architecture that can do inference of the type that I talk about, but still maintain the fluency that we observe in the autoregressive LLMs? That's a challenge. I can't give you an answer, or if I can, it would be speculative because it's not something we've tested.
I think
so. That's a challenge.
There's a challenge to all the PhD students present.
That's right.
And
That's
to work on. It's very exciting times because I remember about a couple of years ago when the first GPT-3 came out, and people were looking at all these kind of emerging abilities of zero-shot learning and so on. And my students were like, what do we do as NLP PhDs? We have nothing to do. But turns out with the more power of these models, we see that they become even more volatile, let's say. Then still not controllable and still very unpredictable. And then there's just a lot of work to control. So I'm really interested when you talk about this kind of the aspect of controllability of your model. Can you elaborate that a little bit more?
Yeah. So if you build, there's a lot of people who are very worried about alignment of AI systems, that if they become too smart, right? How do we make sure that they don't go rogue and kind of escape our control? There's a bunch of fallacies behind this, right? So the first one is that necessarily the minute that a system is intelligent, it's going to want to take over the world. I mean, that's ridiculous. There's no reason to believe this. All kind of reasons to believe that is not the case. But you do want those systems to be controllable, and the way you do this is you hardwire them so that their only possible behavior is a behavior that minimizes a bunch of energy functions or objectives, and you hardwire some of those objectives to make the system safe. So that, I don't know, if you have a domestic robot and it's supposed to be a cook as well, it's going to have to use knives, and you can put a cost function that says, like, don't flail your arms when you have a knife in it and there are people around, things like very simple things like this, right? And then beyond this, you can think of those intrinsic immutable cost functions as laws that the system is intrinsically has to respect, right? It's built in a way that it cannot escape those the minimization of those costs, and that makes them controllable. You just change the cost. So they're not like humans. Humans are difficult to control because we do have intrinsic costs in our brains. We also have trainable costs that basically are the result of education, and which sometimes can be unaligned with the common good, right? So that creates psychopath and things like that. But this is the way. Building cost into our brains, or basal ganglia to be specific, is the way evolution makes us behave properly, or more or less properly. Okay, and then because we live now in conditions that are very different from the ones we evolved in, we as societies have added laws on top of this. So what is a law? A law is nothing more than a new cost function that you need to understand to respect. You're not hardwired to respect it, so it needs to be enforced. But it's basically an additional term in your cost function that says, if you steal, you're going to go to jail, and that's going to cost you in the future. But it's hard to, necessarily convince people that this is an actual cost. Whereas for a machine, it's just a cost that it has to minimize. So it doesn't have a choice. It's not going to be able to, violate whatever law you hardwire into it through the objectives. Now, so that's one thing that's going to make them controllable. That basically will allow us to solve the alignment problem. Now, I'm not claiming that it's easy to solve the alignment problem. Like, how do you define cost functions so for those systems to behave properly? It's going to have to be inevitably an iterative process where you build a system, you put certain costs into it, and then you let it run, and then you adjust, and then you correct. So you're going to have some way of doing this, because there is, inevitably some behavior that you can predict. Now, the second fallacy is the idea somehow that if a system has superhuman intelligence, it's going to want to take over the world. This is completely false. It's not even true for humans. It's not the smartest among us who want to be the chief. Okay, the desire to dominate is maybe linked with testosterone, but not particularly with intelligence. In fact, dealing with a super intelligent AI system is the same as dealing with a very smart human, and or a group of humans. Like, if you are a manager in a research lab, you have a lot of people working with you who are smarter than you, and collectively they're way smarter than you, and that doesn't necessarily mean that they want to get your job. So this idea somehow that as soon as you're intelligent you want to take over is ridiculous. It's just not true.
Yeah, this is obviously I agree with you on that. I have one more question before we go to the audience and give them a chance to ask questions, which is that when ChatGPT came out, actually GPT-3, ChatGPT, and then GPT-4, Sam Altman of OpenAI has said that there's a path towards AGI, right? I always hated this term because what does that mean? There's no such thing. But there seems to be a this race to build models. I wouldn't call it AGI, but at least it's a multitasking model that can do everything under the sun, or most of the tasks. And to me, that seems like there would be a single point of failure, and it's very vulnerable to attack and so on. But when what you're proposing, right? I can imagine we can use the architecture you propose to do different tasks, or we can use it also to build actually an actual AGI, right? So what are you proposing? What are your thoughts on this? Purpose-built AI systems versus so-called AGI models?
Okay, so I don't like you. I don't like the phrase AGI because I don't believe that human intelligence is general. Human intelligence is actually very specialized. We don't like to think of it in those terms. But the reason we think is general is because all of the problems that we can apprehend are problems that we can solve to some extent, right? And so that makes us think that we have general intelligence, but we don't. We're extremely specialized. And I'm not going to go too deep into that question, but we are very specialized. Every animal is very specialized, but we are specialized as well. So there is no such thing as AGI. The question is, will there be at some point machines that have human level intelligence that are as intelligent or more than humans in all the domains where humans are intelligent? And the answer is yes. There is no doubt that this will happen, within the next few decades. But in my opinion, the autoregressive LLMs, as impressive as they are an off-ramp on the highway towards human level intelligence. It's a useful off-ramp, right? So it's something you need to do because it's useful. A lot of people are gonna, create companies and products and things around it that's gonna be very useful to society. So, you need to work on it. But I think it's a distraction towards human level intelligence because of the problems I mentioned. We need to figure out how to train systems from video to learn how the world works. We need systems that can plan and that can reason, that have episodic memory, things like that. So it's a new architecture, right? So there's a lot of research to do. It's good news for PhD students in AI today, which is that, forget about the stuff that people can build products around. Like, you have to work on the next generation.
Right. Thank you. I'm going to take some questions from the audience. Given the time, I'm not sure we can answer all of them, but let's answer some. One question is about your point on superficial reasoning ability. How do you distinguish between true reasoning and pretending to reason, even for human? Even for human, it's true. Like if you look at little kids, right, toddlers, are they reasoning? I mean, they certainly are not really explicitly planning, right? So is that reasoning? Is that pretending to reason? What do you
They're totally planning. We don't think of what they're doing as planning, but they do. Dogs can plan pretty complex actions. Cats, I mean, have you observed a cat looking around, like how to, jump on a piece of furniture? Like they definitely plan their sequence of actions before they do it. And it's pretty complex what they're doing. They have a really, really good dynamical model of their own body. So I think it's the old Moravec paradox that a lot of the tasks that we accomplish we take for granted. We don't consider them intelligent, like vision and like planning simple actions. But in fact, those things are really complicated, and it turns out language is much simpler than that. Okay, now language is treated in the brain by two small areas called the Wernicke and Broca area, one for comprehension, the other one for speaking, essentially, right? And those are like tiny brain areas on each side of behind your ears here, very small. That's what autoregressive LLMs can do. What they can't do right now is the entire prefrontal cortex. This is what makes us smart. Babies can plan. They absolutely can.
So there's a question from the audience that since GPTs can be combined with plugins, now they have plugins such as Wolfram, they can be combined with other plugins, external knowledge source. Do you think it will help?
So there is a number of different techniques that are being proposed for LLMs to use tools. One by my colleagues called Toolformer, and then various other techniques. So yeah, I mean can you, by sort of changing minimally the basic architecture of autoregressive LLM, can you get them to produce queries for a tool and then replace that by the answer that the tool produces. For example, call a calculator to just do arithmetics, which normal LLMs don't seem to be able to do. So yeah, I mean that's certainly a way in the future. But then immediately comes the question of how do you plan the sequence of actions to send to your tool? If it's a simple action, like add two numbers, that's fine. If it's a complex sequence of queries to a database, or writing a program and running it or something, that might be a little more complicated. Although I have to say, LLMs are really good at generating codes. As long as it's not too long, if it's like a page.
Yeah. Another question: when we launch a law, there are always some loopholes. So if we add a term in the cost function, wouldn't there be some pathological mathematical workarounds for the machine to learn and exploit?
Sure. And we'll have to fix it either by manually designing new costs or by training the system, the trainable cost part, so that whatever behavior it did that was inappropriate would be high cost, would become high cost, and then would not be done again. But it's much simpler to do this by training just a cost function than to do this by RLHF, which is the way it's done currently with LLMs, because in that case, you have to retrain the entire model, right? The architecture I'm proposing, you just train the cost. The inference algorithm figures out how to optimize the cost. That's a much simpler problem. But yeah, it's not going to be, it's not going to be like we're going to design a super intelligent system from scratch and then put some cost function and then turning on. It's more going to be an iterative process where we're going to learn how, what proper cost functions to put, so the system sort of does what it's supposed to do and remain submissive, for example, to humans, but not too submissive so that humans can ask them to do dangerous things or
bad things,
steal someone or hack a computer or something, right?
Yeah. Another question: large language models tend to use a simple but scalable model architecture and focus more on the data side, aim to improve the quality and quantity of data. Some people call this as data-centric AI. So there are people who propose to focus more on I think it's Andrew, right? Data-centric AI. There are also the model, the segment anything model proposed by Meta, following this line of thought. What is your opinion about this data-centric AI?
Well, I mean, machine learning is the whole idea of data-centric AI, but the point I think that's important is that you don't want it to be too data-centric, in the sense that humans learn language in a few years with a very small amount of exposure to spoken language and certainly to written language, right? We learn to speak way before we learn to read. Now, if you take the data set that a typical LLM is trained on, like Llama, it's over 1 trillion tokens. If you equate a token to a word, which is not completely correct, but let's assume it's about the same, it would take a human reading 8 hours a day, 22,000 years to read 1 trillion tokens. Okay, so obviously those systems require way more data to learn whatever it is they learn than humans. How can humans learn so quickly? We're obviously missing something huge, right? If we can't now, obviously the memory of the large language models, stores a lot more facts, kind of approximately, which is why they hallucinate. But has read a lot more things, so can use templates for giving solutions to problems that we didn't realize existed, but they exist somewhere on the text, and the system will just regurgitate it to us. So it's a different kind of usefulness or intelligence that we observe in humans. Very, very different.
Yes, there's another question, which is, in your opinion, can reasoning and logic emerge from hierarchical planning, or it can perhaps be just from statistical models with certain latent spaces? For example, different hierarchical latent variables may represent the logic. Are these two approaches actually opposing, or do you think?
No, they're the same. They're the same.
The same
So
thing,
I
right?
think I mean the inference process I described through minimization of energy or maximization of likelihood, whatever, is the same inference process that people have been using in the context of graphical models, factor graphs, probabilistic graphical models, Bayesian nets, things like that. So conceptually, it's all the same thing. You can think of it as a form of reasoning. The main difference, I think, is that because all the modules in the architecture I propose are differentiable, you can do this optimization using gradient-based methods, which is generally much more efficient than using discrete search. Now, sometimes you have no choice, you have to use discrete search. You have to make a hypothesis, am I going to take this action? Is it going to cause this result? Or if I take that other action, it's going to cause that other result. And you have to basically try in your mind, imagine the situation, from sort of discrete qualitative outcomes. But most of the time, when you plan an action, it's done through probably more efficiently through some sort of gradient-based type refinement, if you want. And that's incompatible with sort of classical symbolic approaches. So that's why I'm not particularly fond of what's called neurosymbolic approaches, because as soon as you put symbolic reasoning, you have non-differentiable steps, and that kind of breaks the whole idea of machine learning and gradient-based optimization for inference.
Yeah, indeed. Another question, this is obviously a very PhD student question. Now we have been focusing on transformer architecture. Should we go back to other architecture? This question mentioned LSTM. LSTM can be also part of transformer, but what you are proposing, should we just forget about transformer?
No. What I'm proposing is agnostic about the
actual
architecture that you use inside of those modules, right? Probably the best architecture you can use for the predictor in the JEPA is a transformer.
Yeah.
For the encoders, it probably depends what type of data you're dealing with. So if it's like right now, it's not entirely clear, which works best in the context of images, whether it's convolutional nets or transformers. My favorite approach is actually a combination where the front end is more like a convolutional net and the back end is a transformer. So by the time that the representation is kind of object-based, it makes sense to use transformer because they are equivariant to permutation. So that makes complete sense. But at the low level, in my opinion, it doesn't make any sense to use transformers. Now, what people have been proposing is things like SWIN, for example, which is sort of a convolutional net-like architecture, but each module basically is a transformer-like thing with some attention mechanism. Sure, why not? You could imagine having a convolutional net where the pooling layers are replaced by some sort of attention circuit. I mean, multiplicative interactions is very powerful. And so I think that's a big advantage that you have in certain types of architectures. You don't have to use multiplicative interactions within a transformer, but the fact that you may have them, I think, is very useful. One advantage that transformers have, they have two properties. One property is equivariance to permutation. Okay, that's an important one. The same way convolutional nets are equivariant to shift, transformers are equivariant to permutation of the tokens. Equivariant means that the output result is unchanged. So if you permute the input tokens, the output is also permuted, but otherwise unchanged, right? That's equivariance. Another characteristic that's interesting in transformers is basically that the self-attention mechanism is a kind of associative memory. So there is a process by which, when you have a key and you compare it with a bunch of a query, you compare it with a bunch of keys and then retrieve a linear combination of the values that match. That's like an associative memory retrieval. And if you want to store a lot of information, that's the right thing to do. You probably want a circuit of this type. Now, why should you use that circuit and nothing else? No. And in fact, applying transformers to video, for example, is probably a non-starter. It's just too expensive because it scales with the square of the number of tokens. And so if you have, lots of tokens that represent patches in images and then multiple frames, it gets completely unmanageable very quickly. So there is a lot of innovation to do, I think, in the space of architecture.
Yeah, great news for students. Another
Yeah.
question. Yeah, so we have all this awesome output from AGI, what they call AGI, all these large models or diffusion models. One day, will there be a lot of this output from AI systems on the internet, and then they are going back into the training data, right? And this becomes some kind of a cyclic. I can already see, it's way more easy to generate images than by human artists to paint them. So you're gonna have way more fake paintings from fake artists, meaning paintings from AI than from the real artists. And they will go into the internet and be retrained. So how can we prevent that? Or should we prevent it? And what's going to happen?
Okay, so first of all, it's not entirely clear you want to prevent it completely.
Yeah, that's the question.
Because that's the way human culture works, right? If you think about human culture, different people produce different things, and then other people build on get inspiration from what was produced by other humans. So what you might observe eventually is an evolution of artistic culture due to the fact that a lot of material will be produced by AI systems, and it will naturally evolve because of that. But here is the second thing that's important. It is much easier to be an art critic than to be an artist, okay? So it's easier to design systems that will select what looks good, what needs to be kind of bubbled up and reused, than it is to design systems that actually produce something good. So I think, I don't think that's kind of a major problem. Now, the other thing that you might still want to be able to tell the difference between machine-generated content and human-generated content. And for that, what you need is a system that can trace the provenance and the credentials, basically, of a piece of content. Now, this is important for another reason than artistic culture, but more, whether a piece of content is from a reliable source, whether it's kind of a remix of existing pieces, and then whether credit should be given to the originators of that inspired the piece, things like that. So there's certainly a need for new technology to do this.
Yeah, I mean, electronic music has been around for a while. It's a new genre, and then there will be new genre of AI art, and the people who like those and the people who don't. So I think there will, as you say, it will be part of the human evolution. Another question, obviously, people worry about the future of work. A lot of jobs will disappear. Programming might disappear, for example, and illustration might disappear. Do you have any suggestions for what students should study?
Okay, if none of those trades or those professions are going to disappear, they are going to be empowered by technology, right? So in the sense that your ability to produce a piece of content depends a lot on the techniques that you control. So it used to be the case that you could only be a musician if you were a good performer. And it's not true anymore. Now you can, compose on computers and have synthesizers play the music for you. I think, and it's true also for, painting, photography, right? Things like that. So as soon as kind of a new set of technology appears, it empowers a lot more people to be creative in different ways, right? In new ways. And I'm a frustrated musician. I'm not a very good performer, but I'd love to be, but I don't have to. I'd love to compose music, but it's the same. I've been trained for that. I might have some inspiration for what I want to produce, but I don't have the technique to produce it. And I know a lot of people who are in the same situation who realize, there were musicians or painters, and And when they realize that they will never get the technical level they require to do the art that they want to make, and they get frustrated all their life. So same with science. You can be very good at a certain type of activities in science, but then you might be limited by your ability to program or to do math or something. So what you do currently is that you collaborate with other people who are better than you at those other things. But eventually you'll be helped by machines. And so, instead of being Einstein complaining that he didn't know enough mathematics to do general relativity, which is why it took so long, you won't be limited by this. You might be able to. It will just empower people, I think. So certainly that will cause some professions to disappear or be reduced or be completely transformed. But it will also create completely new professions. Most of the profession that all of us are doing today, maybe not me, maybe not you, Pascal, but certainly all people of the age of your students are doing today did not exist 20 years ago. Okay, like how many web designers are there, right? Or I don't know, front-end programmers or back-end programmers. Those professions did not exist 20 years ago. Or YouTuber, right? Or influencer on Instagram or whatever. Right?
This word didn't even exist. Yes.
Right. So technology creates new profession. It displaces. So the big question is like, how fast is the transition going to happen? And the faster it goes, the more people are kind of left behind, if you want. But economists are telling us that the speed at which technology disseminates in the economy is limited by how fast people can actually make use of it.
Yeah, that reminds me of the recent comments by the Fields medalist mathematician Terence Tao, who said that ChatGPT helps him to find hints on the mathematical problems he wants to solve, but it cannot solve any of this. And then it can provide, can reformat his publications, his the bib tags in his papers and so on. And it's very efficient. It's made his work more efficient, but the essential work of solving a problem is he still has to do it himself because these models cannot do it.
Well, that's true. And but people who use those tools and know how to use them, I think we'd be in a much better position than people who just don't or refuse to.
Absolutely true. Okay, there are many other questions. Let me see. Oh, this is a question. Should we introduce parental controls into LLM-powered chatbots?
I think eventually they will have parental control in the sense that LLM will have there'll be either there'll be autoregressive LLM to the current ones, and they will be trained specifically to interact with young people, or they'll be along the model that I'm suggesting, and there will be objective functions that are specific, appropriate for the person being talked to.
There's a question about medical industry. I would change that question a bit, so it's not about ChatGPT, but in medical industry, this is one area where AI is supposed to provide great benefits. And I would say that today we still have other than radiology, we haven't really seen any breakthrough in the application and to benefit people, And of course, we know all these, large scale models are good for creativity, but, healthcare, medical industry, how can we see more benefit? What other application we can see on the horizon?
So certainly there are enormous benefits in medical imaging because, computer vision works either through segmentation or detection of tumors and things like that, right? So, or the reduction of the time it takes to collect the data for an MRI, which is a project that was done in collaboration with, it's called Fast MRI. It was done in collaboration between FAIR and NYU and released to the world. And now it's being implemented by most manufacturers of MRI machines. They don't have to pay NYU or or Meta for that. It's open source. There's no patents or anything. So I think a lot of applications certainly in imaging. And then there's been quite a few applications also in treatment of chronic diseases, things like diabetes and things like that, where you can sort of measure the effect of certain types of courses of treatment, and then sort of personalize the treatment depending on how the person reacts to it, possibly for other things like cancer and things like this. A lot of promise in drug design, but not really kind of breakthroughs that have landed yet. But there's certainly high expectations for this, because there are startup companies that were bought for a lot of money by larger companies that basically are counting on this. So it's a very, very promising area. And then there are applications that exist today that use LLMs. So they're not doing things like helping diagnose or anything like that, but they help doctors write reports. It's kind of boring. It takes time to write a report. And so you could probably just, type a few facts, and the system will, type a complete report about what you saw. It's useful for radiologists, for example, right? They sit in front of a screen in a dark room, and they see something and they circle it, and then they have to type what it is. But this can be helped. In fact, there's a bunch of startups that have products along those lines.
That's very encouraging. Now we are already over time, so I'm going to ask you one last question. Actually, give you an opportunity to make a closing statement. What do you think is the future of AI?
Okay, so
and application. Where are we going?
Okay, so research, as I said, there is a lot of open questions in research. We do not have a design at the moment for human-level AI. And so that's still very much research. This is not something that's in the hand of industry. If you can come up with a small demonstration, like small scale on a toy problem, that you can train the system to learn hierarchical representations of action plans, and you can do hierarchical planning, I mean, it would be amazing. Or a system that can have the fluency of an LLM, but can also infer an answer by minimizing some objectives. That would be great too, because it would make LLM controllable. So there's a lot of research, science questions to solve there. I think that are very important, beyond just the applications of current technology. Then will we have truly intelligent system in the future? And as I said, the answer is yes. There's no question. And what will be the effect of this on society? And my view of this, I'm a incorrigible optimist perhaps, but my view on this is that this is going to be kind of a new renaissance, basically a new enlightenment for humanity. I don't believe in the singularity hard takeoff thing. I don't think that's real, because there is no such thing as unlimited exponential. They always turn into sigmoids. So I don't believe in that concept, but I do believe that with the help of AI, we'll make progress faster in science and technology, and people will become smarter as a result. There's always this question of if you let school children use calculators, they're not going to be able to do mental arithmetics anymore, and it's going to make them stupid. If you have books, and you can write, you don't need to use your memory as much anymore, right? You can write things down, so you don't need to remember them, and it's going to make you stupid. But it doesn't. It amplifies your intelligence. It makes you more productive. That's it. But it's not going to be like having an AI assistant that works with you is not going to be very different from currently having a whole team of people working for you. It's going to be pretty similar.
On that optimistic note, thank you, Yann, for a great webinar. We have learned a lot, and we hope to have more chat with you in the future. And thank you, everyone, for your questions and attendance. Thank you.
Thanks, everyone.
Thank you. Bye-bye.
Bye-bye.